So what is garbage collection? Garbage collection is an automatic memory management system that identifies and reclaims memory occupied by objects that are no longer needed by your program. Think of it like this. Your computer's memory is like a hotel. Objects are guests checking in. Without garbage collection, once guests leave, their rooms stay occupied forever. Eventually, the hotel runs out of rooms. Garbage collection is the housekeeping service that cleans up rooms after guests leave. An interesting fact: the first garbage collector was invented in 1959 by John McCarthy for Lisp, one of the oldest high-level programming languages. It was revolutionary because programmers no longer had to manually free memory. But why Python needs garbage collection? It prevents memory leaks. Your program automatically frees up memory when you are done with objects, so you don't run out of RAM. Makes your life easier. You can focus on writing code instead of worrying about cleaning up memory. Handles messy situations. Even when objects are tangled up together, Python figures out what to delete. We'll dive into how Python actually does this magic behind the scenes in upcoming lessons. Now let's look at a real-world example. Let's say you are building a web scraper that grabs data from thousands of websites. What happens? Every time you visit a page, Python creates tons of temporary stuff: HTML parsers, data extractors, text processors, etc. Without garbage collection, your program keeps holding all this data in memory, getting slower and slower until crash, probably after just a few hundred pages. With garbage collection, Python is like a smart cleanup crew. It automatically throws away the temporary stuff you don't need anymore, so your scraper can run for hours or even days without problems. Let's see how other languages handle their memory. For example, C and C++, unlike Python, where memory management happens automatically behind the scenes, in those languages, you are the boss. You control everything. Here is how it works. When you need memory, you explicitly ask for it, using malloc or new. You use that memory for whatever you need. And then, and this is crucial, you have to give it back. Forget to free it? Congratulations! You have got a memory leak. Your program slowly eats up more and more memory until... But it gets worse. Check this out. What happens here? Boom! Crash! You are trying to use memory you already freed. This is called a dangling pointer, and it's one of the most common bugs in C and C++. So how does this compare to Python? In C and C++, you manage every single allocation yourself. It's fast, super fast, but one mistake and your program crashes. Python, it handles all of this for you automatically. It's slightly slower, but way harder to mess up. So when would you use C or C++? When you need maximum performance. Game engines, operating systems, embedded devices, places where every millisecond counts and you need total control. But with great power comes great responsibility. Miss one free, memory leak, use freed memory, crash. Now let's look at Java and C#. These languages also have automatic garbage collection, like Python, but they handle it completely differently. Here is the key difference. Java and C# don't clean up memory immediately. Instead, they wait and do it in batches. In Python, this would start cleanup pretty quickly. In Java, nothing happens. The garbage collector is literally taking a nap, waiting for the right moment. Eventually, the garbage collector wakes up and says, "Okay, time to clean the house." And here's the catch. When it runs, your entire program can freeze for a moment. We call it garbage collection pause or stop the world. It's like your program hits a speed bump. Brief pause, then back to normal. So why do this? Why not clean up immediately like Python? Because Java and C# are built for massive enterprise applications. We are talking gigabytes of memory, millions of objects. By collecting garbage in batches, they can be super efficient with huge amounts of data. The occasional pause is worth the overall speed boost. So, when do you use Java or C#? Enterprise applications, Android apps, massive web services, anywhere you are dealing with tons of data and need that high throughput. Just remember, the garbage collector is always watching, waiting for its moment to strike. So we have seen C++, where you do everything manually, and Java, where garbage collection does it all in batches. But Python is different. It uses hybrid memory management. First, reference counting. The fast one. Object not used, freed instantly. Handles 95% of cleanup. Second, cyclic garbage collector. The backup. Runs occasionally to catch circular references that reference counting misses. Why it works? Most objects gone immediately. Tricky circle references caught later by the backup. Best of both worlds, fast and thorough. As you see, C++ gives you total control and maximum speed, but you handle everything manually. Python cleans up instantly most of the time with its dual system, while Java waits and does batch cleanups that can briefly pause your program. Choose wisely, code safely. Alright, time to get our hands dirty. Python gives us a module called GC, garbage collection, that lets us peek under the hood and see what's happening with memory. Let's explore it together. First, let's see the main tools we have. Of course, we're gonna import the module itself, the GC, and then we're gonna use the getCount method. Let's see the result. What are these numbers? These are the object counts in each generation of garbage collection. Remember, Python uses generational garbage collection. Generation 0 is the youngest, where new objects go. Generation 1 and 2 are for objects that survived previous collections. Don't worry, we are going to talk about those generational garbage collection model in upcoming lessons. Let's create some objects and watch what happens. So this is before the creation. Here we create 10,000 objects and let's see what happens after. Now, here is something interesting. You might see the count stay the same or barely change. Why? Because Python's reference counting already cleaned up those temporary integer objects during list creation. The GC count only tracks objects that need garbage collection, like objects with circular references. Here is a breakdown of objects tracked and not tracked by Python's garbage collector. Circular references will be discussed in upcoming lessons. Now let's do a few more actions with garbage collector. We can even turn the garbage collector on and off. Let's have a look. Here, as we see, it is disabled, and here it is enabled. This is powerful for performance testing. You can see exactly what happens with and without automatic cleanup. So the garbage collection module is your window into Python's memory management. You can watch it work, force it to run, or even turn it off completely. As an example of that, there is an interesting fact. Instagram engineers famously disabled Python's cyclic garbage collection in production and relied purely on reference counting. They carefully avoided circular references in their codebase and gained a 10% performance improvement. This shows that understanding garbage collection deeply can lead to dramatic real-world optimizations. The garbage collection module, GC, shows us when garbage collection happens. But how do we see how much memory we are actually using? That's where tracemalloc comes in. Think of it as a memory profiler built right into Python. First, we need to turn on memory tracking. For that, of course, we're going to import tracemalloc and start tracking. From this point on, Python is watching every byte of memory we allocate. Let's create some data and see what happens. Here we are creating a large list and checking how much memory we are using by using tracemalloc get traced memory method. Let's see our current memory and peak memory. The result is we just created 100,000 numbers and can see exactly how much RAM that took. Here is where it gets really cool. You can take snapshots and compare them. Let's first import our tracemalloc, start it. We're gonna take our first snapshot, add some list, like to make changes, right? And then we're gonna make our second snapshot. It's time to compare them with the key type. Line no, we'll see what other key types we have. And let's print the top 3 memory increases. This shows you exactly which lines of code allocated the most memory. Incredible for debugging memory issues. Let's see what key type options we got. First, file name. This is like zoomed out view, which Python files are using memory. If we compare with Google Maps, it shows country view. Second, line no, sweet spot, exact line numbers where memory is allocated, most commonly used. And with Google analogy, it is like street address. Last one, traceback. This is detailed, complete call stack showing how you go to that location. Think of it like a step-by-step directions with every turn. Always remember to stop tracking when you are done. Tracking memory uses a bit of resources itself, so turn it off when you don't need it. Summing up, tracemalloc is your precision tool. While GC shows you when cleanup happens, tracemalloc shows you exactly how much memory you are using and where it's going. Together, they are a powerful combo for understanding Python's memory behavior. I hope this video was useful for you. You can like and subscribe. And thanks for watching.